Most people learn linear regression like this and then move on. But this formula hides almost everything important. When does it work? When does it break? And what is it really doing? So instead of memorizing it, let's build it from scratch. Hi, welcome to my channel. I am Anna, and I break down machine learning concepts simply. Let's get started. We have some data points, and we want to describe them with a line. You can eyeball something that looks okay, but this is not precise. So the real question is, what makes one line better than another? Let's try a few line examples. This one is clearly off. This one is better. This one looks pretty good, but looks good isn't a definition. So we measure the error. Here I use a visualization data points. For each point, we look at the vertical distance to the line. Those are called residuals. To punish big distances more, we square the residuals and average them. That gives us mean squared error. MSE in short. In this example, the MSE is approximately equal to 2.37. Now the problem is clear. Find the line that minimizes MSE. That's the linear regression goal. Our model is just a line, so really we are choosing two values, slope and intercept. Linear regression is just finding the best values for those. You could brute force this, try lots of values, compute the error, and pick the smallest. That works, but it's inefficient. So naturally, the question becomes, can we compute the best solution directly? Let's write the problem in matrix form. We have a dataset X, which is of the dimensions n by d, the number of features. We have also the target vector y, which is of the dimension n by 1. To include the intercept in our model, we can add a column of ones to the data matrix and extend our parameter vector. This allows us to write the model in a compact form as y equal x times beta, where the intercept is just another parameter. So here we can put ones. As I previously mentioned, our goal is to minimize the MSE of beta, which is defined x times beta parameter minus the target vector, where the beta is just beta 1 and a value of intercept. So here are the predictions and here is the target vector. We want to find the parameter vector beta that makes the predictions x times beta as close as possible to the true targets y. Now let's focus only on this value. After using short multiplication formulas, we have something as follows. These two are scalars, so we can write it as follows. So when we expanded the MSE, we get a quadratic function in beta, and minimizing a quadratic is straightforward. We take the derivative and set it to 0, so let's derive it together. So this value does not depend on beta. So after taking the derivative with respect to beta, we end up with an equation like this. This value is like this because x transpose x is symmetric. So now we have the following. These are called the normal equations. Now the solution for linear regression would be this. And we can solve it exactly. But there is a hidden assumption here. This matrix x transpose x has to be invertible. Let's break that. If one feature is just a copy of another, the model cannot tell them apart. The columns are linearly dependent, and now the matrix is not invertible. So, does regression fail? No. It means something deeper. There isn't a unique solution anymore. There are infinitely many parameter values that produce the same predictions. This is where matrix rank comes in. Rank tells us how many independent directions we have. If our columns are not independent, we lose rank. And that's exactly when the inverse stops existing. So now we dive into 3 ways of solving linear regression using first normal equation, the second gradient descent, and then the native sklearn implementation. First, the imports, but they are not important. Now we are creating a dataset, which is just a line with added noise. So the true parameters are 0.9 and 1, which is the intercept. Here we are creating 10 points, and the dataset is looking like this. Now we define helper functions, which is just the line predictions, the MSE error, plot function, and the distance between two vectors. Now let's start with intuition. First, we check a line that is a manual guess. So here, the slope we chose is 0.5 and the intercept is 1.5. Here we have the line that we chose with MSE equal to 2.9661. It's not looking like the best line for this data. Now on to the first method of solving linear regression. It's called normal equation. We add the one column here with the data so that the parameter vector has intercept the b value. As we previously saw, this normal equation is looking like this. So now we have the design matrix, which is the combination of our data and the one vector here. We have 10 points. That is why we have 10 rows here. So here we are using NumPy for the inverse of the matrix X transpose X. And here is the solution for the normal equation. We have lower MSE value than our guess solution, which is equal to 0.3808. And I also wanted to mention that when the matrix X transpose X is not invertible, then the normal equation cannot work because now the rank is lower than the number of columns. And now we can see that the NumPy library cannot find a solution. Now on to the second way of solving linear regression, which is gradient descent. Just to make sure we stay on the same page, we are solving y equals slope times x, which is our data, plus intercept b. And now the gradients with respect to beta parameter, which is combination of m and b, is as follows. I wrote it here. So we are using those definitions. Here, gradient descent iteratively improves the solution until a given threshold is achieved, which means we need to be able to know the ground truth parameters in order to run gradient descent. So if the distance between the ground truth parameters and the gradient descent solution is smaller than the threshold, the gradient descent stops. So now we are using the ground truth parameters found by the normal equations. And here is the solution found by gradient descent with MSE equal to 0.3808. So now the question, did gradient descent actually find the right solution? Here we have the plotted MSE values in terms of the gradient descent steps. And we can see that MSE is dropping very quickly. We previously calculated the ground truth parameters, so now we can see how the gradient descent was choosing the parameter values with respect to steps. We can see that gradient descent pretty quickly found those parameters. I would like to also mention that gradient descent needs tuning of learning rate. So I plotted 3 of the learning rate values, and we ran 3 experiments to see which learning rate gives us the best convergence, which is for the learning rate 0.01. And now on to the last linear regression solution, which is the native scikit-learn implementation. And here we have the solution that scikit-learn found with MSE 0.3808, which is the same as the gradient descent. After each of those three solutions found the parameters, we can compare the line exactly for those three methods. And here are the results. We can see that all of those three methods are pretty aligned, which is a promising thing. We can also compare the exact parameter values that those three methods found, and they are all pretty close to each other. Now we take one step further and compare the time complexity of those three methods. Normal equation needs to build the matrix X transpose X and needs to invert this matrix. Gradient descent has iteration cost, and the number of iterations needed is dependent on the threshold value. Scikit-learn usually uses SVD underneath, and its exact complexity depends on the solver. So now we can plot how much time each method needs when choosing the dataset of size from 10 to 100,000 in a log space sample sizes. And here are the results. We can see that the worst time complexity is for gradient descent method, then for scikit-learn, and the fastest method is for normal equation. And here's an additional plot for gradient descent steps needed, and approximately we would like to have 1,600 steps when running gradient descent for linear regression. And that's it for the implementation. I encourage you to look at the full implementation on my GitHub repository, which will be in the description below. There are a few important limitations of linear regression. As the name suggests, it assumes a linear relationship between the input features and the output. Therefore, it does not capture non-linear patterns, such as quadratic or other curved relationships very well. Another issue arises when features are highly correlated, which can make the solution unstable and difficult to interpret. Lastly, linear regression is not robust to outliers because it minimizes squared error. Large errors are heavily amplified, and the presence of outliers can significantly distort the model. Now, here is the deeper way to think about all of this. We are not really fitting a line. We are taking the target vector y and projecting it onto the column space of the data matrix. This projected is the closest possible approximation in the least squares sense. That is exactly what linear regression computes. Everything that we have seen in 2D extends to higher dimensions. In the same way mathematically, we just can't visualize it anymore. So linear regression is not just a formula, it's an optimization problem, a linear algebra problem, and a geometry problem. And now you understand all three. If you are interested in these kind of topics, subscribe to my channel, leave a comment and like the video so that it reaches more curious minds. As always, you will find all the resources, including the code, in the description below. Thank you for watching and I will see you in the next one. Bye!